So in this session, I'd like to introduce the Gauss's theorems. So this is a very convenient to express the Gauss's law in a differential form. So I'd like to show you the Gauss's theorems. At first, I'd like to prove the Gauss's theorems. So let's S is equal to the S sub 1 plus S sub 2 be a closed surface, yellow and green surface, and divided by these curves. And the upper surface is written the S sub 1, and the lower surface is given by S sub 2. And the total surface is given by the sum of the S sub 1 and S sub 2. And n is a unit vectors normal to the S. So n sub 1 is a unit vectors on the surface of the S sub 1, and n sub 2 is a unit vectors normal to the S sub 2. Upper and the lower surface are denoted by the S sub 1 and S sub 2, and the S sub 1 and S sub 2 are expressed g equal f xy. And the lower surface is expressed g equal gxy. We'd like to consider the volume integral of these quantities, round a sub g, round g. If you use a Cartesian coordinate, it is expressed triple integrals dx, dy, dg. So dx, dy is kept, and the dg, we integrate the dg. Lower limit is g equal gxy, and the upper limit is fxy, because we integrate over this point to this point. Okay, this is g, this point is f. So from lower limit is g and the upper limit is f. Then we could perform this integral. You can just substitute f upper limit and the lower limit is a g. We could consider the dx dy. This dx dy is correspond to this area. This is dx dy. So dx dy areas can be considered projections of this ds ones. This is xy planes, and so perpendicular. This is z axis, and the delta s sub 1. So if you consider this is delta s sub 1, so perpendicular vectors, this becomes n sub 1 vectors. The angle between the n sub 1 and the z axis is a gamma 1. So this is right angle. So this becomes gamma 1. The xy, dx dy is a projection on the xy planes. So this part it becomes dx dy. So from these figures, you can find that the dx dy is expressed delta s sub 1 cosine gamma 1. So cosine gamma 1s, you can express e sub g dot n sub 1 delta s sub 1. Because n sub 1, this is unit vectors. So magnitude of n is 1. Okay, and the e sub g, this is e sub g. Okay, so dx dy is expressed this equation. So this is the first equation. In the case of the second, this part, so maybe it's better to draw the one more figures. This is the axis, xy plane, and the delta, this is delta s sub 2. Then this becomes n sub 2. This is right angle. So this is gamma 2. And then dx dy. So this part is a dx dy. Then angle, this angle becomes gamma sub 2 minus pi over 2. Then you can express dx dy It becomes delta S sub 2 sine gamma sub 2 minus pi over 2. Then you can use the addition formulas. Minus cosine gamma sub 2 delta S sub 2. So it becomes minus E sub z dot n sub 2 delta S sub 2. Okay, so this is equal to these equations. Then you can substitute this into here to calculate the first terms. To calculate the second terms, you need to substitute these ones here. These expressions come to this equation composed of the two terms. A sub g, E sub g times n sub 1, this part. And the second one, this negative sign, the negative sign cancel becomes a positive sign. And the E sub g, n sub 2. And then we could combine these two forms into the single equations. Surface integral of a cross surface A sub g, E sub g dot n. Also, we could use the same method. So volume integral of the round A sub x, round x is expressed as A sub x, E sub x dot n. Round A sub y, round y is expressed as A sub y, E sub y dot n. Then by combining the three equations, we could find these expressions. So from the first part, we have this one. And the second part, we have this. And the third part, we have this one. So we could combine these three equations. Actually, this part exactly equal to the vector A. We'd like to introduce the new operator. We call it del operators or nabla. Del operator is in the vector form. Del operator is expressed E sub x round round x, E sub y round round y, E sub z round round z. So in the component form, you can express it this way. X component is a round x. Y component is a round y. Z component is round z. So if you consider the gradient of any function of f has a three component, x component, y component, z component, because it is directions round f round x, round f round y, round f round z. This is a gradient using the del operators. Also, you can consider the divergence is a scalar product of the del operator with the vectors. Del operator dot A, this is scalar product, round A sub x round x, plus round A sub y round y, plus round A sub z round z. We can express the Gauss theorem is a very simple way. Volume integral of this left hand side is expressed in a very simple ways using the del operators. Scalar product of the del operators and the vectors is equal to the right hand side, this A dot n ds. This right hand side is expressed this one, right hand side. And the ds and the n is combined to express the ds vectors. So it becomes here. So Gauss theorem connects the volume integrals to the surface integrals. Okay, so we use the Gauss theorem to express the Gauss law. So integral form of the Gauss law is a surface integral by E over the cross surface is equal to the Q over epsilon naught. Q is the total net charge inside of the cross surface. You can express with the volume integrals of the charge density of the law. If you integrate the charge density in the volume inside of the cross surface, it becomes actually Q. applying the Gauss's laws. So d E ds, this is surface integrals, is expressed with the volume integrals. This is exactly same. So these two have to be the same. So this means E dV equal 1 over epsilon naught rho dV. So this means if you combine the order term into the left hand side, E epsilon naught is a constant, so rho over epsilon naught dV equals 0. So you can choose any size of the dV. Then actually the inside of this quantity have to be 0 to satisfy these equations. So this becomes 0. So we have this equation. This is a differential form of the Gauss's law. Okay, this is the end of this session.